Imagine ice defying gravity, seemingly moving on its own. Scientists at Virginia Tech have made this a reality, creating self-propelled ice disks that glide across specially designed metal surfaces. This isn't just a cool party trick. It's a fascinating exploration of physics with potential real-world applications. This groundbreaking research, published in ACS Applied Materials and Interfaces, comes from Jonathan Barreko's lab at Virginia Tech. Barreko's team is known for pushing the boundaries of our understanding of how water behaves in its various states: solid, liquid, and gas. A few years back, Barreko's lab made waves by demonstrating a three-phase Leidenfrost effect involving water vapor, liquid water, and ice. You're probably familiar with the Leidenfrost effect, even if you don't know the name. It's what happens when you flick water droplets onto a scorching hot pan. Instead of immediately vaporizing, the droplets hover and skitter across the surface. This is because a layer of vapor forms beneath the droplet, insulating it from the heat. The effect isn't limited to water. It works with other liquids too, like oils and alcohol, each with its own specific temperature threshold. Barreko's earlier work showed that a similar effect could be achieved with ice. By placing a thin, flat ice disk on a heated aluminum surface, they found that at temperatures above 150 degrees Celsius, 302 degrees Fahrenheit, the ice didn't levitate like liquid water. Instead, a much higher temperature of 550 degrees Celsius, 1022 degrees Fahrenheit, was needed for levitation. Below that critical point, the meltwater beneath the ice boils in direct contact with the surface. But cross that threshold, and you get the three-phase Leidenfrost effect. The key here is the extreme temperature difference within the meltwater layer. The bottom is boiling, while the top clings to the ice. Maintaining this difference requires a lot. In fact, ice can suppress the Leidenfrost effect even at very high temperatures. This suggests that using ice particles instead of liquid droplets could be more effective in applications like spray quenching, which is used for rapid cooling in nuclear power plants, firefighting, and metal shaping. But here's where it gets controversial. Some argue that the high energy cost of achieving the Leidenfrost effect with ice makes it impractical for many real-world applications. What do you think? Is the potential benefit worth the energy investment? Now, in their latest research, Barreko and his team have shifted their focus to a more viscous analog of a Leidenfrost ratchet, a method of self-propulsion for droplets. What's different here is we're no longer trying to levitate or even boil, Barreko explained. Now we're asking a more straightforward question. Is there a way to make ice move across the surface directionally as it is melting? Regular melting at room temperature. We're not boiling, we're not levitating, we're not Leidenfrosting. We just want to know, can we make ice shoot across the surface if we design a surface in the right way? The inspiration for this project came from an unlikely source: Death Valley's mysterious sailing stones at Racetrack Playa. These watermelon-sized boulders are scattered across the dry lake bed, leaving trails in the cracked earth as they slowly migrate each season. For years, scientists were baffled by this phenomenon. It wasn't until 2014 that the mystery was solved. Researchers discovered that the ground is too hard to absorb rainfall, and when temperatures drop, this water freezes. As temperatures rise again, the ice melts, creating ice rafts that float on the meltwater. Strong winds then push these ice rafts, carrying the boulders along with them. Nature had to have wind blowing to kind of push the boulder and the ice along the meltwater that was beneath the ice, Barreko said. We thought, what if we could have a similar idea of melting ice moving directionally, but use an engineered structure to make it happen spontaneously, so we don't have to have energy or wind or anything active to make it work. To create their self-propelled ice disks, the team poured distilled water into thermally insulated petri dishes, ensuring bottom-up freezing to minimize air bubbles. They then milled asymmetric grooves into uncoated aluminum plates in a herringbone pattern, essentially creating arrowhead-shaped channels, and bonded them to hot plates. Each ice disc was carefully placed on the plate, and the experiments were filmed from multiple angles. The herringbone pattern is crucial. The directionality is what really pushes the water, explained Jack Topachik, a graduate student in Boreyko's lab. The herringbone doesn't allow for water to flow backward. The water has to go forward, and that basically pushes the water and the ice together forward. We don't have a treated surface, so the water just sits on top, and the ice all moves as one unit. Boreyko compares the effect to tubing on a river, where the directional channels, rather than gravity, drive the flow. You can see how it just follows the meltwater, he said. This is your classic entrainment mechanism, where if the water flows that way and you're floating on the water, you're going to go the same way too. It's basically the same idea as what makes a Leidenfrost droplet also move one way. It has a vapor flow underneath. The only difference is that was a liquid drifting on a vapor flow, whereas now we have a solid drifting on a liquid flow. The densities and viscosities are different, but the idea is the same. You have a more dense phase that is drifting on the top of a lighter phase that is flowing directionally. And this is the part most people miss. The team initially thought that making the surface water repellent would speed things up. But when they coated the aluminum herringbone surface with a water repellent spray, they got a surprise. Instead of gliding smoothly, the disc stuck to the surface for a moment before suddenly slingshotting across the plate. It's a totally different concept with totally different physics behind it, and it's so much cooler, Topachik said. As the ice is melting on these coated surfaces, the water just doesn't want to sit within the channels. It wants to sit on top because of the hydrophobic coating we have on there. The ice is directly sticking now to the surface, unlike before when it was floating. You get this elongated puddle in front. The easiest place for the ice to be is in the center of this giant, long puddle. So it recenters, and that's what moves it forward like a slingshot. Essentially, the water expands asymmetrically, creating a difference in surface tension. The flatter puddle in front has less curvature than the smaller shape in back. When this difference becomes strong enough, it just rips the ice off the surface and flings it along, Boreyko explained. The team envisions several potential applications for this technology. One possibility is energy harvesting. By patterning the metal surface in a circle, the melting ice disk could continually rotate. Attaching magnets to the disk could then generate power. Alternatively, a turbine or gear could be connected to the rotating disk. The effect might also offer a more energy-efficient way to defrost things. If you had a herringbone surface with a frosting problem, you could melt the frost, even partially, and use these directional flows to slingshot the ice off the surface, Boreyko said. That's both faster and uses less energy than having to entirely melt the ice into pure water. We're looking at potentially over a 10-fold reduction in heating requirements if you only have to partially melt the ice. That said, Boreyko emphasizes that the most exciting discoveries often come from pure curiosity. Most practical applications don't start from knowing the application beforehand, he said. It starts from, oh, that's a really cool phenomenon. What's going on here? It's only downstream from that. It turns out you can use this for better defrosting of heat exchangers for heat pumps. I just think it's fun to say that we can make a little melting disk of ice very suddenly slingshot across the table. It's a neat way to grab your attention and think more about melting and ice and how all this stuff works. So, what do you think? Could this self-propelled ice technology revolutionize defrosting or energy harvesting? Or is it just a fascinating scientific curiosity with limited practical applications? Share your thoughts in the comments below.